Let's finish out Chapter 11 by talking about 11.6, graph coloring and chromatic polynomials. Let's say you are put in charge of chemical storage. There's certain chemicals that have to be kept separate from one another, and you're just going to use a graph and some coloring techniques to help you keep these straight. So to use graph coloring, you're essentially going to color vertices a different color if they cannot be stored together. So G has a proper coloring if and only if for all of the vertices that are in your graph, if A is incident to B, which basically means if AB is an edge, then A and B have different colors. That makes sense. So let's take a look. We're going to have a couple of different types of questions we'll see with graph coloring. The first is, how many colors do we need? So it's pretty easy to sort of guess and check here. Let's just say, and I'm going to use the same ones I used in the explanation below. Let's say I color B yellow. Well, if B is yellow, then anything connected to B can't be yellow. So let's call A blue, and E blue, and C blue. Then the question becomes, my only vertex that I haven't colored is D. Do I have to use a different color besides yellow and blue, or can I use yellow? Well, since B is not directly connected to D, I can just use yellow again. Now again, for a very simple example like this, it's easy to come up with a solution of 2 without really breaking a sweat. But what we always want to do is to generalize and to determine what's the best way to come up with our solution besides just guess and check. So again, we'll be looking for 2 different types of things. One is, what is the chromatic number? And the chromatic number is what we were just looking at, which is the minimum number of colors required to color the graph. So in this case, chi-G, which would be the chromatic number for the graph. The other, and we haven't looked at one of these yet, and we won't at first, we're going to focus on this guy first, but we will transition to looking for the chromatic polynomial, which is P, G comma lambda, which will tell us how many ways we can color the graph with at most lambda colors. So that's going to be some number of colors. So what we're going to do is we're going to look at an example and do it together, and then we're going to just generalize our results for each one. So for the first, here is obviously the complete graph for K5. So when we generalize, we're going to generalize for all complete graphs. This one I'm looking for the chromatic number, which is what's the least number of colors that I can use. For instance, I'm going to color this guy green. Then, can I color any of the other vertices green? Well, I can't, because that is connected to every other single one. So let's say I color this purple. Well, can I color anything else purple? No, because it's connected to every other single one. Same thing with blue. I can't color anything else blue because it's connected to everything else. This guy is connected to everything else. This guy is connected to everything else. So it seems pretty clear that I'm going to have, for a complete graph, K5, I'm going to use 5 colors. And in this case, it's going to generalize very easily into any complete graph. So what is the chromatic number for any complete graph? It is just whatever value n is, where again n is the number of vertices. And again, that makes sense because we're dealing with vertices that are connected to every other vertex. Question 2. We're looking for the chromatic number for K 3, 2. Obviously, this is a bipartite graph. What we know about coloring is I can choose any color I want for the first one, but if it's connected, which this guy is and this guy is, I can't color those green, so I have to choose a different color. But the good news is, because the green, everything on this side isn't connected to one another, these guys can all be green. So if it's a bipartite graph, it's always going to be 2 because I have 2 sets and everything in this set isn't connected to anything else in that set, and everything in this set is not connected to anything else in that set. So it's always going to be true that it's 2 colors for a bipartite graph. So far we have only looked for the chromatic number, and the chromatic number was how many colors must we have. Now we're going to switch gears. The rest of the examples are going to be looking for the chromatic polynomial for the graph, and lambda is going to represent the number of different colors. So essentially this graph obviously is not a connected graph. And the question is, how many colors can this vertex be? Well, if I have lambda to choose from, that one can be lambda colors. And because my next vertex isn't connected to it, I can also have lambda colors. And because my next vertex isn't connected to either one of those, it can also be any one of the lambda colors that I have available to me, and the last one, any of the lambda colors that I have available to me. So in general, if it's a graph where no vertices are connected, then I have lambda to the n, essentially. And in this case, n was 4, because there were 4 vertices. Lambda times lambda times lambda times lambda, lambda to the 4th. And again, this is only true for when we don't have any edges. So this is a graph that is not connected at all. It will generalize lambda to the n power. Let's go back to our complete graph, K5. We already did this one previously for the chromatic number. Now we're looking for the chromatic polynomial. So now we're not saying how many colors do we need, we're saying how can we generalize the chromatic polynomial. So we'll start by saying this guy could be lambda different colors, but this guy could be lambda minus 1, because whatever color I choose here, I can't choose for this guy. And this guy can be lambda minus whatever color I chose here and whatever color I chose here, so lambda minus 2. That pattern continues, lambda minus 3, lambda minus 4. So I found it for K5. How can I generalize? Well, to generalize, this little series of numbers should look familiar. This is lambda divided by lambda factorial divided by lambda minus n factorial. And again, that would hold true right here, because lambda minus n would be lambda minus 5, and so the lambda minus 5 on top and on bottom would cancel out. Whoops, that was the top. The lambda minus 5 on the bottom would cancel, and everything else on the bottom would cancel, leaving me with just this. New question. Now I'm looking for the chromatic polynomial for a path and then generalize. So again, if I have lambda colors, this guy can be lambda. This guy can't be whatever color I chose for A. This guy can be any color except for whatever I chose for B, so lambda minus 1. Whoops, my lambdas are getting worse and worse. This guy can be any color except for whatever color we chose for C, so again, lambda minus 1. And this guy can be any color except for what I chose for D. That gives me lambda minus 1 number of colors. So essentially it's lambda times lambda minus 1 to the however many vertices I have take away 1. So for this particular example, we had lambda times lambda minus 1 to the 4th, but essentially for any n path, n vertex path, we're just taking 1 away from that, because with the exception of the very first vertex, each of the others has lambda minus 1 choices. let's take a look at an example where we have a graph with components. And remember, components are essentially separate graphs that are not connected to one another. Then we want to be able to generalize. So let's take a look at my first component. This guy is a connected graph, a complete graph. And so we've already really talked about complete graphs, but let's just look specifically for this one, and then we'll talk about the generalization together. A can be any color I want, which we call lambda. This guy can't be whatever A is, and this guy can't be whatever A or B is. And then the other one, I guess, is really also a complete graph of 2. So this is any color and any color except for E. So our first component is a complete graph. And the second one we could call a complete graph, or we could just call a 2-vertex path. Either one really is going to result in the same solution. So we end up here. But the generalization really is that you should look at each component as its own graph. So this guy was a K3, and this guy could have been a K2, or we could have called it just a path with 2 vertices. But we get the idea that all we're going to do is use the product rule when we're dealing with components. So you're going to find whatever your chromatic polynomial is for each one and then multiply. Here's just one for you to try, and again, this is not one I'm asking you to generalize because this is just a graph. I have 4 vertices. It's not a complete graph, it's close, so I want you to find the chromatic polynomial just specifically for this one. Whichever method you deem most suitable. When you're ready, press play to see how you did. So essentially what I'm looking at is choose anything I want for my first vertex. It's connected to this guy, so anything besides what I chose for my first vertex, anything besides, whoops, why do I keep wanting to draw a K instead? Anything besides what I chose for my first 2 vertices go here, and this guy actually, because he's only connected to 2 of them, is anything except for those 2. So notice in this case I have lambda, lambda minus 1, lambda minus 2, lambda minus 2. And in this one we took it a step further and we said, hey, guess what? Lambda is 6. So if lambda is 6, then I've got 6 times 5 times 4 times 4, or 480 different ways that I could color this if I have 6 different colors at my disposal. Last question for chapter 11, I'm asking for the chromatic polynomial for g comma 2, which of course means how could I color this with 2 different colors? Try this on your own. When you're ready, press play to see how you did. Hopefully we have determined that that is impossible. So I can do it 2 different ways. I can either just say, hey, let's do a guess and check method. Let's color this guy yellow. Well, if that guy's yellow, then this one can't be yellow and this one can't be yellow. So let's call this one green. Now, unfortunately, because it's a complete graph and this last vertex is connected to a yellow and a green, it can't be either of those. It has to be a 3rd color. And therefore, I can see by doing the example, just by guess and check, that this is not going to work. I cannot color it using 2 colors. The other way is, of course, to just talk about it more in generalities and say this guy can be lambda colors. This is lambda minus 1. This is lambda minus 2 because, again, they're all connected. And by plugging in 2, and then 2 minus 1 is 1, and 2 minus 2 is 0, I end up with a solution of 0 ways to color this with 2 colors.